Hello class and welcome to Capstone Design ENME 444. I'm really glad to have you all here. I'm really excited about teaching this class. I have taught this class for, goodness, I think I've said before, something like 25 years, and my experience here at UMBC has been great. You guys know a lot of stuff and you actually put it to good use in this course. Today I'll be talking about sort of an overview of the course, what's involved, how things are going to go and operate, and about the project selection process. And just remember, we have to get those project selection forms turned in today. Now, we've talked about everything you've done before in terms of your coursework that's actually brought you to this place. And now you're here ready to actually go out and build something for a sponsor, which is awesome. But we have to ask the question, how is this going to impact your career? How is everything you've done so far going to impact your career? And one way you can answer that is to ask people who are in those careers or ask people who actually study those careers. So the American Society of Mechanical Engineers has actually done a survey of managers in industry, of people on the job, to try and figure out what are the top skills needed to advance your careers. And according to ASME, what do you think they are? Give yourself a second to think about this. You might be surprised to know that the answer is communication. It's actually none of the technical skills that you learn in your engineering degree. The number one thing that they say engineers need more of is communication skills. And so this course will actually focus on those in spades to get you ready for the job market, and also will tie in, of course, all the technical aspects and the prototyping and testing of the prototypes that you create. So that communication is going to sort of fall under this sort of catch-all of capstone documentation, of which there will be a good bit, but what I try to do is structure it in a way that it will be a little bit easier than what you might see in a standard capstone class, just because we only have one semester and we have to balance that with prototyping, and it's going to be a lot different than you might see in the interdisciplinary capstone class that Dr. LaBerge runs, but they actually have a full year, so they can do this differently than we have. But before we get to start talking about what we're going to do in this class, we can talk about what engineers do on the job and how that ties into what you're going to do in this class. So engineers, they document their process. We're asking that you keep detailed notes throughout all the projects that you work on in your career. And for this project, yes, keep detailed notes on it. You can do this through any type of medium that you sort of works for you, whether that be Word documents, Google Docs, physical notebooks, which actually companies still do give out to their researchers and their technicians who are actually developing things, especially R&D. One reason because it's very hard to transmit physical copies of an entire document off-site, so they can actually keep that stuff locked down and don't have to worry as much about corporate espionage. I've seen a lot of people through this class use that top right, use the sort of electronic notebooks to great effect, very well. So if whatever works for you, try and find something that's going to work. The only thing we say is that loose pages of paper, no good. One, because they get lost. Two, because they're very hard to organize. And three, because it just does not sit well with standard professional practice. Standard professional practice has these sort of orderly documented devices, orderly documented systems that we follow. So engineers document, as well as their process, they document their work. What we're going to do in this class is all the documentation that you develop, we're going to store that on a Google Drive. And we're going to call this thing a design history portfolio. What this means is that if you generate memos or reports, and we'll talk about those in a bit, any budget materials that you keep up with, so Excel spreadsheets, meeting minutes that you take, the presentations you generate, calculations and analyses, if they're done in FEA, great. CAD models, of course, we can keep those. Calculations, if they're done by hand, we actually need to see photocopies of those. You can just take a picture of it. If they're done on one of these electronic notebooks, put it out to a PDF. If it's MATLAB or if it is Mathematica, again, we can PDF those things as well. We want to organize these things into folders. And what we say is start now, doing these sort of using collaboration tools to sort of bring all this stuff together. whether those collaboration tools are, if you want to use Google Drive, we actually prefer that. At the end of the semester, we're going to require everything be put into a Google Drive. So if you actually start with a Google Drive, it actually might be easier because you can just copy it all over. And somewhere in the next few weeks, we'll actually give you, if you're interested, links to that final Google Drive, so you can actually start documenting stuff there, if you will. But you don't have to do that yet. One thing that's interesting about all this documentation and all this process documentation is that it falls out of the need to, if it comes to court, show through patent type litigation when you had an idea, how you came up with that idea. So you can prove it was yours and prove it was yours by a certain date. Also, in this sort of documentation, especially for calculations, analyses, and FEA models, liability. If someone comes back and says you designed a defective part and it's defective by design, that's a huge liability for a company. But if you can show through calculations and analyses and modeling that no, it was supposed to work, and then use that to prove that in use, the user actually did something wrong with it, then that actually helps the company stay out of liability. We're going to have a particular file format that we need to follow. It's kind of here. We're going to give you team IDs. These will not be the project IDs because those, unless all projects run, usually we don't. So I think we have 21 projects or so. So we'll give you a team ID, which will have a different number, but we'll use that throughout the course. So you'll actually sort of get used to using that number. Then the assignment name, and then a version number if you have different versions. Like I said, we'll give you this team ID number, and the assignment names will be things like project number 1, presentation 1, final report, etc. So pretty straightforward. Engineering requires knowledge and research. You cannot know everything, therefore designing things requires that you do research. You have to learn more about the thing that you're getting into, because generally you can't build it based on your existing knowledge, especially if it's something new. And even if it's something you've been working on for a long time, you never want to be stagnant. You want to see if there's anything out there new that can be brought into the work that you're doing. We had to cite all sources of information, including people. Now, please note, Wikipedia is not a reference. It really isn't. You cannot reference that. We won't count that, and it'll actually be a detraction on your grades for the project that require citations. But it can be really helpful in finding references. Why? Because Wikipedia is built by people who ostensibly know something about the topic, and at the end of the page, they'll have a list of references that you can go back to. And so those are primary sources. For product benchmarking, we need you to list the source of the information. If that's a product website, that's fine for products, so make sure you actually cite that. Keep this formatting consistent. We're not going to require any particular formatting system, but in engineering publications, typically IEEE format is followed. So if you want to stick with that one, IEEE, that's a good one. And then you can use Google Scholar after using the library's website. What I find interesting is that people go to Google Scholar first, they run into a paywall, and they say, oh no, we can't get past the paywall. But the library's website actually has subscriptions to lots of stuff. So if you search for it in the library's website, then you can actually possibly get past the paywall, because the library's website will actually have some things paid for already. So like I said, if you go to the library's website, you're almost guaranteed to pull up things associated with your topic that are beyond a paywall. And if for some reason you can't find the stuff there, then use Google Scholar after, and you can see what happens with getting past things to get the PDFs and whatnot that you need. Okay, in that first project memo, when we start talking about that, what you'll see is that you should have a minimum. We'll see that we require you to have citations on the project that you're dealing with. What we will require then is you have 10 of those citations, 10 sources where you actually learn something new about the topic that you're dealing with, or about the project, or about the device, or the system, or whatever environment that or context that it's involved in. If a team of 4, that's about 2 citations per person, so that's not that much. Okay, let's talk logistics. What's going on and how do we get things done? All right, so first and foremost, the Capstone Lab is a room where you can store project materials, you can find resources, tools, experimentation, and testing equipment that you can use throughout the semester. You have full access to it. You can even get keys. To get a key, you have to email Dr. Mink asking for a key. Make sure you CC me because I have to give sort of approval for that, but it's pretty straightforward, and you can use the ever-increasing resources that we have in there. As I go throughout the semester, you'll probably hear me ask you what's in there, what's useful, what could you use more of in that room, and the other sort of fabrication resources through the department, so that we can actually get those things in so you can get more done. Alrighty, let's talk about the big topic for today, capital and logistics. How do we form our teams? Alright, so hopefully you've gotten this information a couple of different ways already, but here we'll present it again just so we're all on the same page. If you have a team or if you're an individual, you got to fill out this form that we've posted for you by Wednesday, the 28th, 11:59 p.m. Fill it out with your top 4 choices. You can find this link to the form through the announcements in Blackboard. You fill it out with your top 4 choices. Let us know preferences high to low from the system that's using the instructions on the form. So within that, if you have a full team or a partial team, submit the form with all team members' names and your team's 4 choices. Do not submit more than 1 form per team. Get everybody together, pick somebody to submit it. That person submits it for everyone. Just makes it a whole lot cleaner. If we get multiple forms for the same group of people, what we end up doing is we use the last submitted form. We've had one issue where different people on the same team submitted the form different times. They had different choices, but we had to go with whichever one was submitted the latest. If you don't have a team, don't worry. Still submit your 4 choices for yourself. So you sign up, you submit it, it's just you, and then what we do is we take all the team information, we take all the choice information, and we consolidate those to form all of our project teams. The way we go about doing this is we use an algorithm, sometimes a genetic algorithm, sometimes we do it by hand, but either way what we do is we maximize the average ranking of projects across all students in the class. So you'll rank things 1, 2, or 3, or 4. What we try and do is give everybody as much as we can, the highest number on their ranking that we can get. I've never had, at least since I've been here, any case where someone didn't get something in their top 4. Sometimes people get 4, sometimes people get 1, but everyone gets something in their top 4 and have not yet had a situation where people don't get something on their list. On Thursday, once we have these project selection forms done, we'll get up and the teaching team will finalize the projects, we'll finalize the teams, and resolve any outstanding issues. So on Thursday, sometimes I gotta contact people quickly, so be on the lookout for emails from me. If you've signed up for WebEx, I'll possibly message you over WebEx, but just look for communication from me, because if I do send you something about team formation, it'll have to be resolved pretty quickly. Project assignments will be announced on Friday, yes, and just to make sure that we show up on Friday if we have class. If not, then I will post another video along with the team assignments, and we'll give some instructions on how to go about moving forward from there. Now, know this, project assignments are final. What that means is once we've decided them, once we've posted them, that's what we're stuck with for the rest of the semester. Hopefully you have something that you like. Hopefully you can find 4 things that you like, such that if you get your first, you get your 4th, you're still not going to be too unhappy getting something that you actually liked, even if it was possibly lower on your list. All right, one more note about selecting projects. There's this concept of, there's this concept of having, using game theory. What does that mean? If there's one project that looks completely amazing, if there are 2 projects that look completely amazing, if there are 4 projects that look completely amazing such that everybody will want them, and you only sign up for those 4, you can almost be guaranteed that it's more likely than not that you're not going to get one of those, because there are going to be more teams than 4 that have to be made, and if there are, then you may not actually get anything on your top list because you haven't sort of picked a backup. So it's kind of like selecting colleges. You have a reach goal. Maybe that's the one you expect everybody's going to go for it. You can sign up for it. Then you have sort of your middle. These are the things that I'd be really happy with. And then you have some of your backups. Maybe that's the fourth one, a backup, which you like, but you don't think other people will. So there's a better chance of getting that if the other ones don't come through. So you can play it how you will, but just keep that in mind. Okay, budgets and prototyping. Budgets. Each team will generally get $200 from the department. This comes from lab fees. That's $50 per person for the class. Outside of that, sometimes the sponsors offer more money. If we have an external sponsor that actually has funds for the project, then they can put something toward it, which is always a good thing. The projects that I run will have additional money available to them. Sometimes the projects that faculty run have additional money to them, but not always. If you're working on the Extreme Motion project, they actually have matching funds going with their projects as well, and so you'll have a little bit of extra money to work on those things. How do we get things fabricated? Well, within the department, we have laser cutting, we have 3D printing with PLA, we have carbon fiber 3D printing. That carbon fiber 3D printing is relatively new. We just got the machine last summer/fall, got it installed middle to the end of the fall, and now we're looking to actually make things with it. The point of that thing is that it can make parts that are 70 or so % the strength of aluminum, which is great, so we don't necessarily have to get things machined. If we want or we need sort of high strength parts, which is a really good thing around here because we have machining capabilities, but we don't have the capabilities to machine a lot of things, and we don't have the capabilities to machine really complex things. But we can make really complex things with 3D printing, and with this carbon fiber printer, we can get them printed and have them be pretty strong. Like I said, we do have the basic machining, mills and lathes via Mr. Mink. So if you have something that has to be machined, you got to make manufacturing drawings. You have to discuss them with Mr. Mink, get his approval, and then if he has the time and the ability, then he'll actually make those things. If not, we use those third-party vendors that I mentioned before, like Send, Cut, Send, and whatnot. And we also have the wood shop on hand. And we have power tools, drill presses, chop saws, table saws, and hand tools in there that you can use. As we go through the rest of the semester, we'll talk about how to get access to the wood shop, how to get access to the capstone lab, like I said, with the key. The wood shop and the laser cutting, the 3D printing, you actually have to work through the lab manager who works with those things. But Emily and Ben, who are the TAs for this term, who will be talking to you in a bit, they will talk to you about the process for doing that. Like I said, other fabrication, third-party resources that are available. We've had really good experiences with Xometry and Send, Cut, Send, getting things machined by them and sent back to us. If you have other issues with sort of things that you have to design to make frames, 8020 is another good resource for that. But we'll talk about this as we get closer to prototyping. Okay, project timeline. The project timeline is really governed by this whole thing called the engineering design process. And I take this from a book by Ulrich and Uppinger called the Product Development book by Ulrich and Uppinger. And their process follows several stages, which I'll talk about now. And we'll work through them over the course of the semester. And we have memos, sort of deliverables that are guided by that particular structure. So the first thing for product development in this design process is the idea that we have to understand and identify what the problem is. So how do you identify the problem, and then how do you formulate that problem into something that engineers can deal with? In this case, we don't have to go into that too much because the problems are being given to you. You don't have to identify it. You don't necessarily have to formulate it. From there, we identify customer needs. What we do is we talk to the people who will be using it. We talk to experts. Less so focus groups and surveys, but those can be done as well. Usually those are for feedback after the fact. But what you want to do is you want to go in and you want to figure out who's using this and what exactly do they need from it. We turn those customer needs into specifications. And what we call these are defining metrics. What can we measure about the thing that will tell us whether or not we've actually reached the goal that we want? And so the simplest one is cost. An interviewer might say it's got to be low cost. We have to turn that into a specification. What is low? Maybe low is $15. And once we know that, we can take that and call that's our target specification for something like cost. We might have them for mass, for strength, for speed, all sorts of things. Yeah. Once we've established those target specifications, we put them into what's called a needs metrics matrix. Sometimes it's called quality functional deployment, QFD. I've been told you've heard of this, which is great. We can benchmark our target specs against the competition to see how well we might fare, and maybe we need to adjust them. And then we can set high and low values. What's our target that we want to shoot for? What's the maximum that we think is worth going for if we can reach it? And then there's minimally acceptable values. We cannot go below this, because we have to do that because there's always trade-offs. All right, once we have these target specifications, we define what this thing should accomplish. Now we have to go about figuring out what it's going to look like and how it's going to do that. So we generate product concepts. We can do this through brainstorming, and then I will also talk to you about why brainstorming doesn't work from a neurological standpoint. Other concepts that I use are brainstorming and this thing called a 6-3-5 method. We'll do some activities in class. Once we have these sort of concepts sort of laid out in terms of all the different ways that we might be able to do something, then we have to sort of take that and reduce it down to something else, into concept combination tables. Let's say, all right, if we have 10 different ways to do the subsystem 1, 10 different ways to do subsystem 2, 10 different ways to do subsystem 3, now we've got a multitude of combinations that we could put together for subsystems 1, subsystem 2, subsystem 3 by picking different ideations or concepts from the groups that we've developed. So we can actually come up with a lot of different possible designs by mixing and matching the ideas that we've come up with for all of our multiple subsystems. Okay, we'll also begin to understand our concepts through black box diagrams, function structure diagrams. So I've been told you've learned about those before as well, which is awesome. So we can go from there. Alrighty. Once we have all of our ideation methods done, once we understand this thing through our function structure and black box diagrams, maybe we've even come up with concept combination tables to mix and match our subsystems to come up with possible designs that put different things together, then we have to do concept selection. And so we take all these possibilities and we screen them. Pew matrices, I've told you've heard about that. And then we, once we have the Pew matrices done, we've screened things, we've sort of gotten rid of the lower half. Now we sort of look at what's called an AHP, analytical hierarchical process method, where we give scores and weights to the different specifications and the different customer needs, and then we try and figure out how well each of our concepts may fit one of those, and that allows us to rank everything based on these concepts and come up with a total score. Once we have that total score, that then becomes the thing that we try and move forward with. Once we move forward with it, the next thing is to generate prototypes, and we'll talk about many different ways to do that. 3D printing, mills, and lathes. Our initial prototypes will possibly be made out of cardboard and paper and duct tape, because Alpha 1 prototypes, the first ones we make, those are quick and dirty. They're really just high level, just to give you the most basic understanding of the thing that you're dealing with. When we begin to talk about prototypes, we'll talk about tolerancing, design for manufacturing, critical part counts, and all these different things that go into making an engineering product. And after that, generating basic drawings so that we can actually begin to manufacture the real thing. Alrighty, finally, we assess our prototype once we've actually made it to make sure that it meets our target specifications, to make sure it meets our customer needs, and if it doesn't, then we have to refine it and kind of go around this whole cycle again. So the cycle is pretty straightforward at a high level, but once you put it into practice, you kind of see all the steps and how they might map onto the project that you're dealing with. And all throughout the whole process, we have to deal with teamwork. and we have to deal with ideation work. And there's some theories about that, about how you get the best ideas out of a team, how you have teams work together in a more efficient manner, and we'll talk a little bit about those. But basically, these 5 steps that come from a company called IDEO, who is well known in the late 80s, 90s, early 2000s for being a development firm that was able to create some very notable products across a range of design, or I should say a range of not necessarily fields, but a range of product lines. So they've done everything from toothbrushes to shopping carts to hand tools, all because their process of generating good designs is what makes them very valued and makes them effective. It's not necessarily what they make, it's how they go about doing it. So one of the key things that they, or I should say 5 of the key things that they promote are encourage wild ideas at the beginning, defer judgment. Everybody gets to throw ideas in, and you don't talk about good, bad, or indifferent at the beginning. You build on others' ideas, so not just your own, so that everybody contributes their own thought processes to everything. And then you understand human behavior. What that means is you got to understand how group dynamics work and how individuals can either bring groups up or bring groups down, and really keep track of that throughout the semester. And finally, you got to care about the consequences. So when you come up with something, how is that going to impact all the other aspects of your design? Does it meet the needs? Does it meet specifications? How hard will it be to build? How hard will it be to test? Right? All of that sort of stuff. And as you probably have already worked with, we'll deal with Gantt charts. And you may not have worked with, we'll deal with this thing called a critical path analysis. Critical path analysis is essentially what are the steps that we need to get from point A to point B? How long will each of those steps take? And which of those paths then becomes the most important one, the one that takes the longest amount of time or has the most uncertainty. And generally what you want to do is identify that path early and put more people working on it. And I need you to stop and listen for a second, because the critical path, that is the modal category for critical paths in capstone projects that I've worked with, is anytime you have a hardware-software interface. That usually is the place where things break down for teams trying to get software to integrate with hardware, even in this day and age where many things are plug and play. So if you have a project that involves that, what I would strongly suggest is put one person on that from day one. That's their goal, that's their job, that is the thing that they are tasked with figuring out. And I would also say they don't do anything else. All they do is spend all their time doing that, because historically that's the thing that doesn't get done at the end for those projects, if something doesn't get done. Okay, project timeline. So what we're dealing with here is we've got 3 phases of development in this project, or I should say in this course. On the right hand side you can see a list of line items. You can probably tell that there's a date column on the left, and you may or may not be able to tell that there's columns of topics and assignments on the right. And what we do is we break this class up into these 3 phases, and those 3 phases have their own deliverables, they have their own presentations, they have assignments associated with them, they may or may not have lectures associated with them, but you can find that schedule here through this link, detailed course schedule, probably not a link in the video, but if you pull up the slides, or if you just go to Blackboard and look for where it says schedule, you can pull it up and see where we're at right now and what's coming up. Each of these phases has specific deliverables, and those due dates are actually on the schedule, and they're on the assignments in Blackboard. Those 3 phases are target specifications and concept design. That's what we're in now. We've got to figure out what it is we have to make and what it has to do and what it's going to look like. Prototyping and detailed design, that's when you try and make the thing the first time and refine the way that we make it. And then final prototyping, testing, and documentation. Final prototyping, that's when we get the thing to work. We test to see how well it works, and then we refine it to make sure it works the way we want it to. And that documentation is where we sort of bring all together, all the documentation that we've been working on. Now, along the way, we'll be doing documentations in phases 1 and 2, but that final documentation is the final report, final presentations, and final demonstrations. So we kind of lump that all together there. So what is phase 1? Well, in phase 1, we call that requirements, definition, conceptual design. We're going to learn from the customer. We'll learn from the market, the products that are out there. Like I said, you determine what you have to do. You determine the specifications you got to meet. You generate the concepts. You down select to figure out which ones to move forward with. And then we move on to our next phase. What are the requirements for this phase 1? The written deliverables, we have a team contract. We have project memos 1 through 4. You can run project memo 1 is a problem statement, prior art. So we got to learn what we got to do, and we got to figure out what's already been done. The next, we develop our customer needs, the mission scenario, black box, and functional block diagrams. We'll review what those are, and they help us understand the scope of the project. We turn those needs into specifications. We develop our needs metrics matrix, the QFD, a work breakdown structure, which allows us to lay out all the tasks to get to work completion, and then we put that all in a Gantt chart. Number 4, design concept, evaluation, and selection. So after we've done some ideation, we come up with all our different designs, we present those different designs, and we present the way in which we select which one we're actually going to move forward with. We don't just pick something and say, this looks good. No, we do it in a rational manner. So we do our Pew matrices for screening, and then we do our analytical hierarchical process to have 1 or 2 bubble to the top. And then we move forward with the best of those. We have project presentations also in this section. We have individual stand-ups. These are just project tech checks. You can check online for a format for those things, and please do follow that format. We have the design concept evaluation and selection presentation, which is that one where we say, okay, what are the concepts you're going to move forward with, and what have you down selected to? That is a formal presentation, and it's the first big presentation of the semester. Okay, for phase 2, prototyping and detailed design. The purpose is to take your design and the target specifications you have for that and try and move it into a working prototype. You want to prepare for building and testing the final system. So we do these prototyping things to figure out what it's going to look like, how or some difficulties that we might have in putting it together. We try and figure out how we're going to get this thing made. Our deliverables are 2 alpha prototype presentations. For these are the sort of very baseline prototype presentations. It may just be CAD, it may be something you've made out of cardboard, it may be something you made out of foam or foam core, but we'll talk about the purpose of these prototype presentations at the beginning. But it's our initial attempts to actually put this thing into some physical, or I should say, some visualizable 3D structure, whether it's something we can hold or something we manipulate on the computer. We'll have 2 of these informal stand-ups, and then this concludes presentation-wise with 1 beta prototype presentation, or I should say a preliminary design review. Here we have something that should be up to functioning. It may not actually meet all your target specs, but you should have something that actually works to some extent so that we can evaluate how the progress is going, how it looks like, whether or not you're going to be able to finish this thing. This one says informal, but it is not. It's actually formal, so that's actually a mistake on this particular slide. We have project memo 5, which is a memo associated with that preliminary design review. So it's essentially a written version of that presentation that just went before it. All right, our final phase, phase 3, fabrication, testing, redesign. And pulling together our documentation. Here, we're going to build and test your complete system, demonstrate that your system meets target specifications, present your design to the public and to your customer as the purpose for our deliverables, a final project report, final project presentation toward ASME judges from ASME Baltimore who come in every semester. We'll have our design showcase. Demonstrations, we'll have those in the atrium. Our presentations will actually be in, I think it's called the theater, in the building directly across from, or one of the buildings across from the engineering building. Additional demonstrations as needed. So we'll try and get your final demonstration proof of functioning in the design showcase as the ASME judges move around, as I move around. But if we need additional demonstrations, if it's not completed by then, we'll schedule those. And then we'll have that Google Drive with your final design history. All right, well, that is it in a nutshell, a pretty big nutshell. Please complete those design project signups by 11:59 tonight, and that would be Wednesday. And if you have any questions, please post them to the discussion board on Blackboard, and I'll answer them there. That way everybody can see the answers. Looking forward to seeing you all in class, and take care.